Alright, in this video we're going to look at using Euler's method. There was a great deal of narrative about what Euler's method is and kind of how it works and the mechanics behind it that you want to read through before you get to example 1. But we're going to start right here with example 1. We're going to use Euler's method to approximate the value of f of x at x equals 1.5. For dy dx equals x plus y, and y of 1 equals 1, using a step size of dx equals 0.1. So the first thing we're going to start, I usually make a table when I do this. I have my x's, my y's, I calculate my dy dx, and then I use this formula here to calculate the next y in the sequence, which then gets dropped down into the next row of the table. So we're told that the initial value when x is 1, y is 1, so I'm going to put 1 in here. And now dy dx is x plus y, so that's just going to be 1 plus 1. So dy dx would be 2. And now I can find my new y by taking my previous y plus dy dx times dx, which in this table is 0.1. And that's just going to give me 1.2. And that I'm going to drop down to be my next y. And I'm going to continue this process until I get the value of y for x equals 1.5. So I go to my dy dx. I've got 1.1 plus 1.2 gives me 2.3 for my approximated value of dy dx at that moment in time. And so I've got my current y plus dy dx times dx. It's going to give me 1.43, which I'll drop down, and that'll be my next y. And then I go ahead and I calculate dy dx. It's going to be 2.63. And so now I've got current y plus dy dx times dx. That's going to give me my new y. It's going to be 1.693. As I'm doing this in this example, I keep getting an extra decimal digit every time, so sooner or later I might need to break out my calculator to help me with this. Alright, so now I'm going to take my, find my dy dx, so that's going to be x plus y. Again, because we're dealing with the differential equation, dy dx equals x plus y here. It's 2.993. And so now I need my current y plus dy dx times 0.1. And that's going to give me my new y value. 1.693 times 2.993 times 0.1, 1.9923. I'm going to carry that down to the next row of my table, 1.9923. And now I'm again going to calculate my approximated value for dy dx. Here. That's going to be 3.3923. And so I take my current y plus dy dx times 0.1. And go ahead and calculate that. We've got 1.9923 plus 3.3923 times 0.1. And I get 2.33153. And that's the y value that I'm looking for. And so I'm going to approximate this at about 2.332. And that's how I use Euler's method. Alright, Let's go on to the next example, which is actually an AP problem from the AP exam that utilizes Euler's method in it. We're given a table of values and a bunch of information. We're going to actually do parts A and B as well as just a little refresher of some things that we've done before. First, we're going to write an equation for the line tangent to the graph of f at x equals 1. In order to do that, I need two things. I need the value of the function at 1. We're told in the lead up that f of 1 is 15. And I need the value of the derivative at 1, which I can get from the table. That's 8. And so my tangent line is going to be y minus 15. Come on. Where are you, 5? There you are. Is equal to 8 times the quantity x minus 1. There's my tangent line for part A, and I want to use this to approximate f of 1.4. So f of x is equal to 8 times the quantity x minus 1 plus 15. So to find f of 1.4, and now we're going to substitute 1.4 in here for x, and go ahead and calculate it. We've got 8 times 0.4, which is 3.2, plus 15, gives us 18.2 for our approximate. Alright, next, part B, we're supposed to use a midpoint Riemann sum with two subintervals of equal length and values from the table to approximate the integral from 1 to 1.4 of f prime of x. Use this approximation to estimate the value of f of 1.4. Okay, so midpoint Riemann sum with two subintervals. So we're going to use the interval from 1 to 1.2 and the interval from 1.2 to 1.4, and we're using midpoint values for the heights. And so we're going to approximate that the integral from 1 to 1.4 of f prime is equal to the width of the intervals, which is 0.2, and it's uniform, so I can just use a quantity here, and then the values at the midpoints, 10 and 13, and doing the calculations, we approximate that this integral is 4.6, and then to find f of 1.4, or approximate f of 1.4, remember f of 1.4 is equal to the value of f of 1 plus the integral from 1 to 1.4 of f prime. And so f of 1 is given here as 15. And so I'm going to take 15 plus 4.6. I'm going to approximate this value as 19.6. Alright, and then in the last step, we're going to use Euler's method, starting at x equals 1, with two steps of equal size to approximate f of 1.4. So we want our dx to be 0.2 here. So I'm going to go ahead and set up a table here. We've got our x's, we've got our y's, we've got our dy dx, and then we've got our new y, which is equal to our old y plus dy dx times dx. And we're going to start at 1, and we're going to use step sizes of 0.2. I have to scroll back and forth a few times to gather information here. First of all, when x is 1, y is 15. That was given from the problem stem. Now I need dy dx at x equals 1 in order to do this calculation. And I pull that from the table. That value is going to be 8. So dy dx is going to be 8 here. And so I use my old y plus dy dx times dx to get my new y. And that gives me 16.6 as my new y. And then I need the value of dy dx at x equals 1.2. So again, I'm going to scroll up and get that. At 1.2, dy dx is 12. Put that in here. So now my new y is going to be 16.6 plus 12 times dx. And that ends up being 19. And so my Euler's approximation at 1.4 is going to be 19. Alright, we'll stop this video here, and we'll look at the last example from this lesson in the next video. See you guys next time. Have a great day.